Last time we talked about two scenarios in which order matters. We still have to talk about the two scenarios in which order doesn't matter. In this lecture, we're only going to talk about one of those, and that is combinations. So last time we used the word permutation. Permutation is without replacement, and order matters. Combination is going to be without replacement, and order doesn't matter. Next time, we're going to talk about the balls and bins scenario. We are doing replacement there, and order does not matter. But on this lecture, we're going to focus on combinations. So examples will be choosing subsets. Okay, so I have a set of, say, 10 things, and I want to pick a subset that has 5 things in it. So in that case, I'm going to have 5 experiments. The first experiment is going to be the first number I choose. And then the second experiment is going to be the next number that I choose, and the third experiment will be the third number I choose. And in that situation, I'm not replacing things. If I, say, have the numbers 1 through 10 and I choose 5 for my first number, then it's gone. I can't pick it again to be in my subset again on the second choice. So this is without replacement. It's also picking teams. I have 10 people. I'm going to make a basketball team. That means I'm going to choose 5 of these people. Order doesn't matter. I guess if I'm going to pick the people who are going to go on the team, then order doesn't matter. If you're picking people and telling them what position they're going to be, then order might matter. But I'm just going to pick 5 people. I have 10 choices. I'm going to pick 5 of them. I'm going to do it without replacement. Right? I'm not going to pick the same person to be on my team in 2 different spots. So these are examples of order doesn't matter and without replacement. So last time for permutations we had NPR. This time for combinations we have NCR. We could call this an R combination of N things. So if I have 10 people to choose from, I'm going to choose 5 people to be on my basketball team. I'll call that a 5 combination of 10 things, or 10 people. So we could also call this N choose R, because I have 10 people and I'm choosing 5, so we could say 10 choose 5. This is a different notation for the same thing, N choose R. These are also called binomial coefficients, so kind of a lot of terminology and notation to go along with the numbers that we're dealing with now. Don't worry about this part yet, we're going to do that in the next lecture. So a few things to notice, right? So we haven't figured out what N choose R is, but we can notice, even without figuring out what it is, that N choose 0 is 1, right? So I have N things. How many ways are there for me to choose 0? Well, there's only one way for me to choose 0, which is to choose 0, right? There are no other options. There's only one way to choose 0 of something, which is to choose 0 of them. Okay? N choose N is also equal to 1. Is if I have N people and I'm going to choose N people, the only way to do that is to choose all of them. Okay? And also, this is not so obvious, but N choose R is equal to N minus 1 choose R minus 1 plus N minus 1 choose R for 0 less than N and 0 less than R less than N. Okay, so it's an important restriction for the choices of N and R for which this hold. So this has to be N minus 1 and R minus 1 have to be defined, and of course N minus 1 shouldn't be less than R. If I have N minus 1 choose things to choose from, I can't choose R of them, right? So I have this formula for these choices of N and R. So why is this thing true? Let's say I have N things to choose from, and I'm going to choose a subset of size R. So let's say I'm choosing people for my team, okay? And I have Bill as one of the possible choices. So I'm going to have a set of size N, and Bill is one of those things in the set, one of those people in the set, and I'm going to choose a subset of size R. There are 2 types of sets which include Bill and sets which do not. Okay? So let's say if I want to choose a subset of R things which include Bill, well, that means I'm going to choose Bill, and from the remaining N minus 1 people, I'm going to choose R minus 1 of them. How many ways are there to do that? Well, there are N minus 1, choose R minus 1. So there are exactly this many ways for me to choose a team with R people that includes Bill. Right? So I choose Bill, and then from the remaining N minus 1 people, there are this many ways for me to choose the remaining R minus 1 people. Okay? How many ways are there for me to choose a team that does not include Bill? Well, if I'm not including Bill, then I'm going to choose all R of my people from the other N minus 1. So I'm not choosing Bill. That means I have N minus 1 other people to choose from. And there are many ways for me to choose that. Okay? So, subsets which include Bill is this many. Subsets which do not include Bill is this many. And the total number of R subsets, by definition, how many ways are there to choose R people from N people? It's this. So now, if I just add the subsets which include Bill to the subsets which don't, I get this identity C here. In order for everything I just said to be valid, we have to be in this situation. So we have Pascal's triangle. So if I take these three identities, I can fill out Pascal's triangle. So what I'm going to do here is say n corresponds to the row that I'm on. This first level is n equals 0, the next two is n equals 1, the next row is going to be n equals 2, n equals 3, etc. And now every diagonal line here is going to correspond to an r value. This first diagonal line corresponds to r equals 0. The next diagonal line corresponds to r equals 1. The next diagonal line corresponds to r equals 2. So the fact that this first diagonal line is all 1s comes from the fact that n choose 0 equals 1. Okay? So for all of these on the first diagonal line, the r is 0. So all of these are just, that's 0 choose 0, 1 choose 0, 2 choose 0, 3 choose 0, 4 choose 0, etc. They're all going to be 1. Okay? The fact that this diagonal over here is all 1s comes from the fact that n choose n is 1. Okay? This is 0 choose 0, 1 choose 1, 2 choose 2, 3 choose 3, etc. So that's the reason I know I can start with all those 1s is because of these two identities. And now, this tells me how to fill in everything else. So, more precisely, it tells me that whatever should go here should be the sum of the two things above it. So 1 and 1 is 2. Okay? So here we're using 2 choose 1 is 1 choose 1 and 1 choose 0. Which is those two. So these two things sum up to be that one. Okay, that's it. These two things are those two things, and they sum up to be that. Okay. So next, the 1 and 2 is going to give me a 3. 2 and 1 is going to give me a 3. The 1 and 3 is going to give me a 4. The 3 and 3 is going to give me a 6. The 3 and 1 is going to give me a 4. 1 and 4 is going to give me a 5. 4 and 6 is going to give me a 10. 4 and 6 is going to give me a 10. And then another 5. These should be on this row. They're not horizontally aligned. But everything is, on the sides I have 1s, and then everything else is just the sum of the two things above it. Right? So 3 is 2 and 1, this 10 is 6 and 4. We can fill out the triangles, and now very quickly do these computations, and now I can very quickly figure out what 5 choose 2 is. So I go to 5, and then I go to the r equals 2 diagonal line. Okay. N equals 5, r equals 2. 5 choose 2 is 10. Okay. So this is Pascal's triangle. It's very important, very useful if I want to compute some of these values. So down here I have it written. So we haven't actually come up with a formula for n choose r yet. It's n factorial over r factorial times n minus r factorial. How do we know that this is correct? We can actually prove it by induction. It's because I have these recursive facts, but these recursive facts include base cases and then everything else. Okay? So you can actually prove by induction that any collection of numbers which satisfy these properties have to be equal to this, because this you can check manually satisfies these three identities. Okay? So we have a good idea of what the correct answer should be. You can do a check and guess, or guess and check method, as by showing that this function of n and r satisfies these three identities, and that's good enough to show there's a unique solution to these three identities. It has to be this thing. Okay. There's another way to come at this, which I think is pretty interesting, easy to understand. Right. So I know how many n permutations or r permutations there are of n things. Right. So I want to know how many r combinations there are of n things. So here the permutations mean order matters, and I want to know what if order doesn't matter. If order doesn't matter, then we're going to count multiple things multiple times. So if I have 10 things to choose from and I want to choose 2 of them, the permutations consider 1, 1, 2, and 2, 1 to be different things. For the permutations, order matters. So 1 and 2, 1, 2, and 2, 1 are considered different when I'm counting permutations, but if I'm counting combinations, order doesn't matter. 1, 2, and 2, 1 are not considered different things. So if I try to count permutations, I count things in multiple times. So let's see. what's the best way to explain this? I have this written here. So if I have a list of all of the R subsets, right, I want to know, what is this capital N? Okay, how many R subsets are there? That is what we're trying to count here. Is I have a set of N things. I want to choose a subset consisting of R things. How many ways are there to do that? So let's just say, well, let me label those subsets. I don't know how many there are, but I'm just going to pretend like I've labeled them. Okay. And now I want to say, well, if I take each of those subsets and permute the members, each subset has R things, so I can take those R things and permute them in R factorial many ways. Okay. So I take those subsets and then make a group of permutations by taking the elements in the subset and permuting them. Okay. So what I've done here is I've taken the sets and associated with each set of R things a set of permutations. Now in these boxes, I'll get all the permutations, and there are this many, right? Because in the boxes I'll have R permutations, so there are things here. I'm going to get an R permutation of N things here, and this is the total number of R permutations of N things. So if I count the number of things in all of the boxes total, I get this many. And each box contains R factorial things, because if I take these R things, there are R factorial ways to permute them. So I know total in the boxes, there are this many things. Each box has R factorial many things, so I can count the number of boxes by dividing the total number of things by the number of things in each box. And that's exactly what this is. N factorial over N minus R factorial is the total number of permutations in all of the boxes. I divide that by R factorial, which is the number of things in each box, and that tells me the number of boxes, which is the number of R combinations, the number of subsets of size R. So a quicker way to explain that is, if I want to do choosing in two stages, first I choose R things, and there are in choose R many ways to do that, and then there are R factorial ways for me to permute the R things that I chose. And if I choose R things and then permute them in all the ways that I could permute them, that gives me all of the permutations. Okay, so if I do N choose R times R factorial ways to permute the R things that I chose, that gives me all of the R permutations. So that's what's written here. This many ways to choose R things, R factorial ways to permute the R things that I chose, and all together that gives me the total number of R permutations, which we computed in the previous lecture. So, let's see. The main takeaway from this is N choose R equals N factorial, R factorial, N minus R factorial. And let's put that in our box here. So in the previous lecture, we figured out what should go in these two. So here we want to do without replacement, and order doesn't matter. This is N choose R, which can also be written in R like this. And it is N factorial over R factorial times N minus R factorial. Okay. And the next lecture, we're going to fill in this box.